So what happens when the current flows through that? Okay, when the current enters this point, so the current gets divided, so only a small amount of current flows through the galvanometer, where the rest of the current, large amount of current flows through the shunt resistance without damaging the galvanometer. So this is how we are going to convert a given galvanometer into an ammeter. Okay, so next is regarding how we are going to convert a galvanometer into an voltmeter. Okay, so the answer for that is nothing but a galvanometer can be converted into a voltmeter by connecting a suitable resistance in series with the galvanometer. Okay, so what we are going to do is we are going to connect a galvanometer into a high resistance. So we are going to connect the galvanometer into an voltmeter by connecting a suitable high resistance in series. Okay, so you can see here R is a resistor. Okay, which has a high resistance. Okay, and G is a galvanometer, and Ig is the current through the galvanometer. So as you can see here, when the galvanometer is connected with a high resistance in series, so what happens? Only a small amount of current flows through it. Okay, so hence what happens? The galvanometer won't get damaged. Okay, so this is how we are going to convert a given galvanometer into an voltmeter. The rest of the thing is mathematical part. It is said that if you want to convert a given galvanometer into an voltmeter of the range from 0 to any voltage. Okay, so how we are going to convert? So R is nothing but it is a series resistance, G is a resistance of galvanometer, and Ig is the current for full scale deflection of galvanometer. So now since you know that the potential difference across the combination is written as V is equal to Ig into G plus R. Okay, V is equal to Ig into G plus R. What is G? G is the resistance of the galvanometer, and R is the resistance of the wire which is connected in series. Okay, so V is equal to IR, right? According to Ohm's law, that is what we have written there. Ig is the current. Okay, so V is equal to Ig into G plus R. So the next is G plus R is equal to V by Ig, or R is equal to V by Ig minus G. Okay, so this is the mathematical form. Okay, how to convert a given galvanometer into an voltmeter of a given range. Okay, so this is regarding the 2 marks and 3 marks questions based on the chapter moving charges and magnetism. Okay, so the next question is regarding the chapter magnetism and matter, so we will discuss it later. Okay, I hope you people have gone through the 2 marks and 3 mark questions of moving charges, right? In case if you have any doubts regarding any question, okay, or else any 5 marks derivation, you can ask, or else we will move to the 5 marks question of this chapter. So I'll share the another file. Okay, coming to the 5 mark question of this chapter is nothing but it starts with 13th question. Okay, you can see there. So which is that? Which is a very important question where they usually keep asking this one. Okay, in your examination. So that is nothing but derive the expression for magnetic field at a point on the axis of a circular current loop. Okay, you need to find the what is the value of magnetic field at a point on the axis of a circular loop. You can see this is a circular loop here. Okay, and this is the axis, and we have taken a point P which is situated at a distance x from the center of the loop. Okay, so capital R is the radius and I is the current. Okay, so what we have done is first we are going to take a small element. Okay, which is taken as dl. Okay, so a small element dl. So we are going to find what is the value of magnetic field at point p due to this small element what we have taken. So how we are going to calculate it? We are going to make use of this Biot-Savart law. Okay, so from Biot-Savart law we have studied that how to find the magnetic field at any point considering the small element, right? So in the same way we are going to find this. Okay, so as you know that the direction of magnetic field. Okay, so due to the small element and we need to find the magnetic field at point p. So the direction of magnetic field at point p will be always perpendicular to the position vector a and the small element what we have taken. Okay, so db is nothing but the magnetic field at the point p. Okay, so that db, that is the magnetic field direction, will be always perpendicular to the position vector A and the current element. Okay, dB will be perpendicular to vector A and vector dl. So you can see in the figure. So this is the direction of magnetic field. Okay, this is the direction of magnetic field. So the next what we had done is we have just resolved. Okay, so if this is the angle theta here, obviously even this angle will be theta. Okay, they have taken as alpha, so you can take that as theta, alpha, anything. Okay, so if this is alpha, obviously this angle is also alpha. So now what we are going to do is we will resolve the dB into two components. Okay, so this dB into two components. So what happens, one will be, that is will be along the uh, one will be dB cos alpha. Okay, the another one which will be along the axis will be dB sin phi, sorry, dB sin alpha. Okay, so perpendicular to the axis of the loop component will be dB cos alpha, the component along the axis of the loop will be dB sin alpha. Okay, so this is how we are going to resolve. Okay, so the next is mathematically we need to prove that. Okay, so it has been given that consider a circular coil carrying current as shown in the figure. Let capital R be the radius of the current loop, I be the current in the loop, dl is nothing but it is the length of the current element AB. Next, x is a distance of point P on the axis from the center of the current loop O. Okay, there is nothing but the explanation of the figure what I said. So next here, what we are going to do is, in order to find the magnetic field at point P. Okay, initially what we are going to do is, before resolving the dB into two components, what we are going to do is we are going to make use of this Biot-Savart law. So I need to calculate the value of magnetic field at point P due to the small element dl, that is, which is AB. Okay, so A is a position vector. So now I'm going to apply the Biot-Savart law. So according to the Biot-Savart law, the magnetic field at the point P will be dB is equal to mu naught divided by 4 pi IDL sine theta divided by A square. Okay, so theta is the angle between the current element, I mean theta is the angle between the element and the position vector. Okay, so theta is the angle between the element what we have taken, small element and the position vector. So you can see the current element, that is nothing but AB. Okay, AB and position vector A always makes an 90 degree. So as you know that sin 90 is how much? Sin 90 is nothing but it is 1. So hence when theta is equal to 90 degree, so the value of dB comes out to be as dB is equal to mu naught divided by 4 pi into IDL divided by R square plus X square. Okay, so how did we calculate this A square value? Just apply the Pythagoras theorem. So consider the triangle BOP. Okay, BOP, consider the triangle BOP and calculate the value of A. Okay, so by considering that you can calculate the value of A. So A square comes out to be as R square plus X square. So in the place of a square, so we have substituted the value of r square plus x square, which is considered as equation 1. Okay, so now as I said, we are going to resolve the dB into two components. As you know that the perpendicular component will be dB cos alpha, and the that is the component which is along the axis of the loop will be dB sin alpha. Okay, so now as you know that when you take the two diametrically opposite element, okay, so I'll take this small element AB and diametrically opposite current element I'm going to take. Okay, so when I take two diametrically opposite elements, so what happens, the when you solve the dB again, okay, when you draw a position vector, if this is A, so obviously the direction of magnetic field will be in this direction. So if this is angle alpha, again this will be angle alpha. Again, if you resolve this dB, okay, into two component, what happens, one will be along the axis of the loop and one will be along the perpendicular to the axis of the loop. So the perpendicular component, which is dB cos alpha, gets cancelled out. Okay, so the dB cos alpha of two diametrically opposite element get cancelled out, and only the dB sin alpha component of the two diametrically opposite elements add up. Okay, so making use of that, you can write here, so it has been given very clearly. You can see there, this magnetic field dB vector can be resolved into two components, that is dB perpendicular is equal to dB cos alpha, and dBx is nothing but equal to dB sin alpha. If the magnetic field at P is summed over the entire loop, all the perpendicular component, that is dB perpendicular, are cancelled out. That is the dB cos alpha get cancelled for opposite diametrical element. Okay, for a diametrically opposite element, the dB cos alpha get cancelled out, only the dB sin alpha gets add up. Okay, so hence to find the magnetic field at point P due to the entire current loop, what we are going to do is we are going to integrate, or we are going to do the summation for this dB sin alpha. Okay, all the dB sin alpha is summed up or integrated. So here they have taken the summation sign, it's one and the same. Okay, even you can take the summation sign, or else even you can take the integration sign. So now what happens? This comes out to be as B is equal to summation dB is equal to summation dB sin alpha. That is nothing but equal to summation of what is the value of dB. So according to equation 1, it is mu naught divided by 4 pi IDL divided by r square plus x square into sin alpha. Okay. So this is the value of B now. So now what we are going to do is B is equal to summation of mu naught divided by 4 pi IDL divided by r square plus x square. So now what we are going to do is, considering the triangle, we are going to find the value of sin alpha. Okay, so from the figure you can find the value of alpha. Okay, you can find the value of sin alpha. So the value of sin alpha comes out to be as r divided by r square plus x square to the power of 1 by 2. Okay, that is what we have substituted here. So the next is B is equal to mu naught divided by 4 pi IR divided by r square plus x square to the power of 3 by 2. You can see there here we have r square plus x square in the denominator and r square plus x square to the power of half in the denominator. If you multiply that, you are going to get r square plus x square to the power of 3 by 2. Okay, it is nothing but like 1 plus 1 by 2, which comes out to be as 3 by 2. Okay, so next, now we are going to integrate only the current element dl. Okay, so summation of dl is nothing but equal to the circumference of the loop, that is 2 pi r. Okay, you can see here mu naught divided by 4 pi into ir divided by r square plus x square to the power of 3 by 2 into 2 pi r. Okay, so now substituting that value, you are going to get b is equal to mu naught divided by 4 pi 2 pi r square I divided by r square plus x square to the power of 3 by 2. So this is the value of magnetic field at point P due to the considering the whole loop. Okay. So if you just go through the derivation, you will come to know that at point P, the magnetic field due to a small current element is nothing but equal to this one, which is equation 1. That is the magnitude of magnetic field at point P due to a small current element dB. Okay. So in order to calculate the magnetic field at the point P due to the whole element, what we have done is we have done the summation. So hence this is the value of magnetic field at the point P due to the entire current loop. Okay. So as I said, this is the important derivation which they ask for 5 marks. Okay. Just go through. In case if you have any doubts, you can ask. Just go through the figure carefully. Next, go through the mathematical steps. In case if you have any doubts, you can let me. So go through for few minutes. Yes, any doubt, students? Or else shall we move to the next question? Okay, fine. We will move to the next. That is, derive the expression for the force between two infinitely long straight parallel conductors carrying currents, and hence define ampere. Okay. So even this is a important question, 5 mark question. Okay. So from this chapter, you are going to get two 5 mark question. One is nothing but it is circular loop, and one is this one. Okay. So even you have uh, the other questions, but usually repeatedly they have asked this two question itself. Okay. So see here, what we need to find is we need to find the force between the two infinitely long straight parallel conductors carrying current. Okay. So for that, what we have done is, let us take the two conductors, okay, which are the straight parallel conductors which are infinitely long. Okay. So the current through the conductors B, that is the conductor, I mean the current along the conductor 1 is nothing but denoted by I1, and the current through the second conductor is denoted by I2. Let D be the distance between the two conductors, which is very small compared to the height of the conductor. Okay, compared to the length of the conductors, the distance is very small. So now what we are going to do is, as you know that when you take a straight conductor, the magnetic field produced will be in the form of circular loop, right, which is according to the right hand thumb rule. So now what we are going to do is we need to calculate the magnetic field value. Okay, that is B1. Okay, so for that we are going to make use of this. So B1 is equal to mu naught divided by 4 pi into 2I1 divided by D. Okay, so this is the value of magnetic field due to the current flowing in the conductor, first conductor, okay, which is I1. So magnetic field comes out to be as B1 is equal to mu naught divided by 4 pi into 2I1 divided by D. Okay, so next is nothing but it is said that now the current carrying conductor B is in uniform magnetic field. Hence, magnetic force on the segment L of the conductor B is, say, as you know that whenever you place a conductor in the presence of magnetic field, so what happens, it experiences the force, right? So what is the magnitude of force experienced by the conductor when it is placed in the presence of magnetic field? It is the expression F is equal to BIL sin theta, right, which we have already derived. Okay, so F is equal to BIL sin theta is the force experienced by the conductor when it is placed in the magnetic field. So now what we have done is we have considered the conductor 1, okay, and the magnetic field produced by the conductor 1 is B1, and the expression for that is nothing but this one. Okay, so now as you know that we have placed the second conductor also. Okay, so now what happens, the conductor 2 experiences the force, right, due to the magnetic field produced by the conductor 1. So now what we are going to do is we are going to write that one as F is equal to I2 L B1 sin theta. Okay, so as you know that now what we are going to do is, what is the value of theta? Theta is nothing but the it is the angle between the current and the magnetic field. Okay, so it makes an angle of 90 degrees, so sin 90 is nothing but equal to 1. So hence the value of F1 comes out to be as F1 is equal to mu naught divided by 4 pi into 2 I1 I2 divided by D into L. Okay, so similarly if you consider the second conductor, okay, so even the second conductor is a straight conductor, so what happens, the magnetic field produced will be in the circular form. So the value of that can be written as same as this itself. So that can be written as B2 is equal to mu naught divided by 4 pi into 2I2 divided by D. That is the value of magnetic field. Okay, so the next is force experience can be written as in the same way F2 is equal to mu naught divided by 4 pi into 2 I1 I2 divided by d into L. Okay, so hence the force experienced by both the conductors is nothing but same. Okay, so hence what happens when the two conductors are placed together, okay, where the current flowing through the both the conductors is along the same direction, so the force experienced by the conductor will be nothing but it will be a attractive force. Okay, so assume that if the currents are anti-parallel, if the current directions are anti-parallel, so what happens, the two conductors experiences a force of repulsion. Okay, suppose if the current flowing is parallel, the direction of current are parallel. Okay, at that case what happens, the two conductors which is placed closer, okay, experiences the force of attraction, and this is the force of attraction. Okay, since you know that the direction of current is same, so now we need to define the definition of ampere. Okay, the definition of ampere comes out to be as thus: if two very long straight parallel conductors of negligible cross section carrying steady current are placed 1 meter apart in free space, experience a mutual force of 2 into 10 power minus 7 Newton per meter length of these conductors, then the current in each conductor is said to be 1 ampere. Okay, so when do you say that the current flowing through each conductor is 1 ampere? Okay, it is said that the current flowing through each conductor is 1 ampere when the distance between the two conductors is 1 meter and when the two conductors are placed in free space. Okay, at that case the force experienced by the two conductors is nothing but equal to 2 into 10 power minus 7 Newton per meter length, and hence we say that the current flowing through each conductor is said to be 1 ampere. The distance should be 1 meter apart. Okay, and it should be placed in the free space, that is the vacuum. So this is the definition of ampere. Okay, so even this is a 5 mark question, just go through once. In case if you have any doubts you can let me.